Hello there, Mrs. Saunders here. Welcome to the Epic Saga of Calculus, where we're not just solving problems, we're telling a story. You see, mathematics is not just a set of rules, it is truly a story, a living, breathing narrative that stretches across continents and centuries, a drama filled with curious questions, brilliant minds, bitter rivalries, and world-changing ideas. And at the heart of that story is calculus. Too often, students ask, when will I ever use this? That's a fair question, but before we get to how calculus is useful, let's ask, why was it developed in the first place? Calculus didn't just appear out of nowhere. It grew slowly out of real human problems. Problems that thinkers wrestled with for thousands of years. How fast is something moving right now? Can we measure something infinitely small? And what happens as we get closer and closer to a value that we can never quite reach? Let's begin our saga, not in a modern classroom, but in an ancient coastal city of Italy. It's the 5th century BC, and a philosopher named Zeno has just proposed a paradox, so mind-bending, so frustrating, that it shook the very foundations of how people thought about motion, distance, and time. Can Achilles, the fastest man alive, ever catch a turtle? Zeno's famous paradox begins with a race. A swift-footed warrior, Achilles, is chasing a tortoise. The tortoise is given a small head start, and Zeno argues that Achilles will never catch it. Why? Because first, Achilles must reach the point where the tortoise began. So let's call that point X. But in that time, the tortoise has moved forward, perhaps not terribly far forward, but Achilles now has to get to that point, and so on. Every time Achilles arrives where the tortoise once was, the tortoise has moved a little farther ahead. And this continues forever in the paradox. But in real life, we know that, well, Achilles will catch up. Zeno's claim wasn't that Achilles might never actually catch up, but he insisted that it was logically impossible because the process requires completing an infinite number of tasks in a finite time. This wasn't just a joke or a brain teaser, it was a serious philosophical argument, one that questioned the coherence of motion itself, and more than that, it questioned the nature of infinity. Today we resolve this by recognizing that infinite geometric series can have finite sums. We'll learn more about that later. But in Zeno's time, the tools to make sense of this, they didn't exist. There was no formal language for limits, no notation, no algebra, and perhaps most importantly, no comfort with infinity. To the ancient Greeks, infinity, it was dangerous. It threatened the perfection of mathematics. I mean, numbers were supposed to be whole, rational, and complete, and infinity was none of those things. Zeno's paradox had mathematicians and philosophers stuck at the edge of understanding. It wasn't just about Achilles or a tortoise, it was about whether mathematics could actually describe the real world. And for centuries, there was no clear answer. But then, in the 4th century BC, in what we now call Turkey, a mathematician named Eudoxus brought a new idea to the table. Say hello to the underappreciated genius of ancient Greece. While everyone else was arguing about turtles, he was doing geometry, like on hard mode. Eudoxus wanted to measure the immeasurable, to calculate areas and volumes of curved shapes that had long defied Greek geometry. The tools of the time could handle squares and triangles, but what about circles, parabola, the shapes of the natural world. To address this, he developed what we now call the Method of Exhaustion. And the idea was revolutionary. Let's start with a shape you can't measure, say a circle, and then fill it with shapes you can measure, like a square, and then a pentagon, and so on, and so forth. As you increase the number of sides, the polygon fits more closely to the curve. The error, or the leftover space, just becomes smaller and smaller. Mathematically, this is the beginning of a profound idea. You don't need to calculate something exactly all at once. You can approach it, approximate it, and then take that approximation to the limit. This method allowed Eudoxus to exhaust the difference between the polygon and the true figure. He didn't call it a limit, but the seeds had been sown. One of the most powerful applications of this method came a century later through the work of Archimedes in modern-day Sicily. Archimedes extended the method of exhaustion with extraordinary precision. He used it to approximate the area of a circle, the volume of a sphere, the surface area of a paraboloid, results that wouldn't be formally proven again until the invention of integral calculus. He also used this method to estimate the value of pi. To do this, Archimedes took the inscribed polygons that we already have and also circumscribed polygons around a circle up to 96 sides. And he computed upper and lower bounds and squeezed pi between them. Now, we're not going to cover the specifics of that right now, but this was not just clever geometry. It was a mathematical analysis in its infancy. It was the act of enclosing a truth between two narrowing boundaries. It was the birth of approximation with rigor. Yet even with this brilliance, neither Eudoxus nor Archimedes could cross that final threshold of Zeno's paradox. They lacked the symbolic power of algebra, the tools of functions, and that precision of modern notation. They were circling the ideas of limits, but without formal definitions. Their work remained geometric and not analytic. Still, their legacy is unmistakable. Zeno posed the problem, Eudoxus gave us a method, Archimedes brought the ideas to life, and calculus, though still 2 millennia away, was beginning to take shape. In the centuries that followed, mathematical thought grew slowly. Greek geometry was preserved and expanded in the Islamic Golden Age. Indian mathematicians explored infinite series, but the full resolution of Zeno's challenge, the unification of motion, infinity, and approximation, that would have to wait. Not until the 17th century, when a young Englishman found himself locked away during a plague, would these ancient ideas be transformed into something new, a new mathematics of change, a calculus. But that is a story for episode 2. Zeno's paradox may have shaken the ancient world, but it didn't stop there. Over centuries, mathematics just kept chipping away at the mystery of motion and change, and eventually, 2 brilliant minds working continents apart would ignite a revolution in mathematics. So next time on the Epic Saga of Calculus, we'll talk about the plague, rivalry, and the birth of something brand new. Thanks for being here.